Demystifying all-flash arrays on endurance, a longevity perspective by Patricia Florisi. This is a story about the hazards of shortening media life endurance in all-flash arrays. Hazards mainly caused by write amplification, which are unnecessary writes done by the storage system that cruelly reduce the lifetime of the storage media and brutally increase its total cost of ownership. Hazards that can be simply prevented by meticulously dodging, circumventing, bypassing, and avoiding altogether any unnecessary writes to the media. And that is exactly what the next generation of all-flash arrays are architected to do. Ready to learn? Let us face the menaces. The first secret, not so secret about flash, is that unlike disks where data can be literally overwritten on top of existing data, flash technologies require the data to be erased first before new data can be written to the flash cells. The second secret, not so secret about flash, is that unlike disk, where data can be written an indefinite number of times on the same position by simply remagnetizing it, there is limited number of program erase or PE cycles before a flash cell wears out. As a result, flash arrays need to increase the lifetime or endurance of flash technology by minimizing the number of times data is written. In other words, reducing the number of times a cell goes through a PE cycle. Since the storage array has no control over user date writes, the only way to increase endurance is by minimizing overhead in the number of times the array itself causes user data to be rewritten, commonly referred to as write amplification. In other words, write amplification occurs when a single user data write is augmented or amplified by additional writes performed by the storage array itself. And why would the storage array perform any write amplification in the first place, you may ask? Well, for many reasons actually, but many of them are historical, where poor design choices for flash arrays have been unwisely copied from the design of disk arrays, where endurance was not a concern. But for all flash arrays, write amplification can be lethal. Oops! Not a good idea. And here is why. First, let us consider garbage collection, which is triggered when an entire block of flash cells needs to be erased so it can be written into again. There are two types of garbage collection. Drive level, where the garbage collection is performed very efficiently by specialized logic in dedicated ASIC processors embedded in the solid-state drive or SSD, and system level, where the garbage collection is embedded in the logic of the array controller. While there is no reason whatsoever for all flash arrays to implement system-level garbage collection when drive-level garbage collection is available and on, many do, causing chunks of user data to be copied into temporary location, the erasing of the entire block of cells, and then the rewriting of the user data, amplifying the number of writes of that data into the storage by one every time a system-level garbage collection occurs. Oof! It's not only a lot of work, but also causes an unnecessary increase in the PE cycles because the drive-level garbage collection will kick in when storage space needs to be reclaimed. Second, let us consider deduplication, which consists of identifying data chunks that are identical and storing just one copy in the array. There are two types of data deduplication: offline and always inline. Offline deduplication works by storing all the data first. The system then periodically scans the array to find duplicates and delete them. Oops! Not a good idea in general, because the system stops user rights to find and delete duplicates, severely impacting the performance. This is especially harmful for flash technologies because it increases PE cycles every time duplicate data is deleted. Always inline in-memory deduplication, on the other hand, works by checking before the user data is written into the array whether the same content already exists. If so, the data is not written at all. Amazing, right? And that's not all, because next generation all-flash arrays implement an efficient, blazingly fast way to check for duplicates based on its content addressing storage technology. And how does that work, you may ask? Well, whenever user data write request arrives, the data calculates a unique signature and searches its content-based address placement mapping to check if the signature already exists. If it does not, it creates an entry for that signature, sets a reference counter to 1, and then writes the data into the array. If it does exist, it increments the reference counter by 1 to indicate the number of write requests for the same data, but it does not actually write the data again to the storage array. That's it! With always inline in-memory data deduplication and content-based data placement, no duplicate data is ever written, regardless of the number of times the duplicate appears. None. Zippo. Nada. Niente. Period. And that's not all. Far from it, because content-based data placement is also used to balance data placement across the array. For every signature created, the array uses its last several digits to map which cell the data will be stored at, seamlessly balancing data placement across the array with no post-processing, without increasing write amplification and allowing the array to scale in balance. No additional writes for balancing the data. None, zippo, nada, niente, period. Wow! Third, let us consider space-efficient snapshots, which are point-in-time copies of production data used to provide a variety of data services, including backup. Typically, administrators would schedule applications to freeze for a short period of time, take a snapshot, and then resume operations. These snapshots would then be backed up to external devices. In a redirect or new unique write method, new writes cause the existing data to be copied or snapshotted to a snapshot area, and the new write overwrites the existing data. Oops! Not a good idea in Flash media. Since data cannot be written in Flash, the new write is performed in a new area, and the existing copy is marked as deleted to be garbage collected later, decreasing the endurance of the media. In content-based data placement, new writes do not overwrite the existing data. Instead, they are literally redirected to another storage space, and metadata is updated to indicate the locations of both the changed data and the unchanged snapshot data. Wow! Much better approach for Flash, since there is no data copy or overwrite, right? But that's not all. Far from it. Because next generation all-flash arrays are designed to maintain metadata in main memory, not in Flash. Updates to the metadata do not cause any write amplification at all. And again, Wow! But that's not all. Far from it. Because some array designs deploy offline implementations of yet other data services, such as data compression, rebalancing of data across the array, and standard rate protection. There is a huge negative impact on media endurance. Oops! Not a good idea, right? And yet, that's not all. Far from it, because all of these offline operations and system-level garbage collection procedures fuel each other in an unending cycle, violently accelerating the demise of the array endurance. In summary, the next generation of all-flash arrays is carefully designed from its conception to maximize flash endurance by avoiding write amplifications where always inline in-memory deduplication avoids any duplicate data from being written in the first place. Content-based data placement automatically balances the data across the array, avoiding any post-processing to move data around. Device-level garbage collection only instead of together with system-level garbage collection eliminates any additional PE cycle usage. Space-efficient snapshots eliminate data copying and overwrites. Inline compression stores already compressed data. Flash-optimized data protection delivers superior data protection with faster performance than RAID 10, for example, and more. Once again, EMC is strategically positioned to enable you to capitalize on all of the benefits of all-flash arrays by minimizing write amplifications and increasing endurance and longevity. So take the time to learn more today about EMC innovative technologies that maximize all advantages of flash technologies. EMC's new Extreme I/O all-flash arrays, built from a clean sheet architecture specifically designed for flash. EMC's new Extreme I/O data protection, which protects data from SSD failures, but also delivers unique and important benefits in performance, consistency, flash endurance, data integrity, and simplicity of operation. EMC's new Extreme I/O data reduction powered by inline global deduplication and compression, providing an average of 6:1 data reduction. EMC's new Extreme I/O space-efficient writable snapshots that provide petabytes of effective flash capacity in scale-out arrays. EMC's new Extreme I/O write efficiency methods that, when combined with the use of superior enterprise-grade eMLC flash, extends flash longevity by 20 times, and EMC education services and consulting to help you increase the endurance of your flash arrays. EMC technologies empower you to really harness the value of flash for your applications and virtualization strategies through all flash arrays and more.